The scientists at NASA calculate with incredibly large numbers, as they must deal with distances that span the universe. In order to do such calculations, they rely on mathematical models to help them evaluate expressions where numbers approach infinity. Hi, my name is Tom Atwater, and that's what we'll be delving into in today's lesson: finite and infinite limits. Let's start off with a definition. Definition of a horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. We say that as x approaches infinity, what we mean is that as x moves increasingly further to the right on the number line. And when we say as x approaches negative infinity, we mean that as x moves increasingly further to the left of the number line. Let's look at an example. Use graphs and tables to evaluate the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x, as well as identify all horizontal asymptotes for f of x is equal to e to the negative x divided by x. Let's take a look at the graph first. Here's the graph. It's in two pieces like this. And we can see that as x goes to positive infinity, the value of f of x goes to 0. And as x goes to negative infinity, we see that the value of f of x goes to negative infinity. What that means is that y equals 0, that is the x-axis, is a horizontal asymptote. All right, great. Let's try another example, and this time let's approach it by using the sandwich theorem. Once again, find the limit as x goes to infinity and as x goes to negative infinity, as well as find all the horizontal asymptotes for the function f of x is equal to sine x divided by x. Okay, so here's a graph of what this looks like. F of x sine x over x. And what I want to point out on this graph is you can see that the heights are getting smaller and smaller as x goes to either end. All right. Well, what that would make me want to say is that we would see that the function is approaching 0. It's getting closer and closer to the x-axis. And the same thing coming out this way. It's getting closer and closer to the x-axis. But let's see if the sandwich theorem can help us determine that for sure. With the sandwich theorem, we should take the sine x over x and look at that compared to the absolute value of 1 over x and the absolute negative, the absolute value of 1 over x. When we make that comparison, what we'll see is that as x goes to infinity, positive infinity, that once again, this expression goes towards 0. And as 1 over x goes to, as x goes to negative infinity, that this expression here also goes to 0. Which means that sine x over x, the limit as x goes to 0, as x goes to infinity, is 0 because it's sandwiched between those two limits. So the graph is supported by the sandwich theorem that we solved algebraically. Great. Now let's turn our attention to the properties of limits. Properties of limits as x goes to plus or minus infinity. if L, M, and K are real numbers and the limit as x goes to plus or minus infinity of f of x is equal to L, and the limit as x goes to plus or minus infinity of g of x is m, then we have the sum rule that tells us that the limit as x goes to plus or minus infinity of the sum of f of x and g of x is simply equal to the sum of their limits. Then we have the difference rule, which says if the limit of x goes to plus or minus infinity of f of x minus g of x, that is the difference between them, is just going to be equal to the difference between their individual limits. We have the product rule, as the limit as x goes to plus or minus infinity of the product of f of x times g of x is equal to the product of their limits. And we have the constant multiple rule that says the limit as x goes to plus or minus infinity of k times f of x, where k is a constant, that is simply equal to k times L, the limit of f of x. The quotient rule says that the limit as x goes to plus or minus infinity of f of x divided by g of x is simply equal to the quotient of their limits, provided, of course, that m does not equal 0. And lastly, we have what's called the power rule, which says if r and s are integers and s does not equal 0, then the limit as x goes to plus or minus infinity of f of x raised to the power r divided by s is simply equal to L raised to the r divided by s, provided, of course, that that L raised to the r divided by s is a real number. All right, great. So that's all the properties we have. Let's look at a definition of a vertical asymptote with respect to limits. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a from the right-hand side of f of x is either plus or minus infinity, or the limit as x approaches a from the left-hand side, the negative side, of f of x is plus or minus infinity. I think, again, the best thing to do here is to try an example and show how to apply this particular definition. So let's find the vertical asymptotes of the graph of f of x. Then describe the behavior of f of x to the left and to the right of each of the vertical asymptotes. And the f of x that we're looking at is x squared minus 2x all over x plus 1. So what the first thing we should notice is this is going to have a vertical asymptote where x equals negative 1, because that would make the denominator 0 and therefore make the fraction undefined. So then what we want to do is look at what happens as x approaches negative 1 from the positive side. And as x approaches negative 1 from the positive side, what you would notice is, for example, take negative 1/2 as something you can substitute in. That's going to be a positive number here because we'll square it. This is going to be positive because it's a negative times a negative. And the bottom, negative 1/2 plus 1, is also positive. So what that means is that as x goes to negative 1 from the positive side, that f of x is going to positive infinity. And if we look at x going towards negative 1 from the negative side, then f of x is going to go to negative infinity. And so that's the behavior we have at the vertical asymptote of x equals negative 1. Let's now move on to a general statement using limits to determine the end behavior for any function. The function g is a right end behavior model for the function f if and only if the limit as x goes to infinity of f of x divided by g of x is equal to 1. And the function g is a left-end behavior model for the function f if and only if the limit as x goes to negative infinity of f of x divided by g of x is equal to 1. Well, with many of our theorems and definitions, it's best to illustrate them by looking at an example. So let's do that here as well. Show that g of x is equal to x is a right-end behavior model for f, and that h of x equaling e to the negative x is a left-end behavior model for the function f of x is equal to x plus e to the negative x. Okay, so what we need to do is apply that definition that we just looked at. So what we need to do is look at the limit as x goes to infinity of f of x divided by g of x. And in this case, we know that f of x is equal to x plus e to the negative x. And we were told to use g of x equals x. Well, of course, then we're looking for this limit, but we can separate this out and say x divided by x is 1 plus e to the negative x over x. And what will happen is, as we look at e to the negative x over x, well, as x gets really, really big, that is, as x approaches infinity, then this particular part of it will approach 0. And therefore, this limit is 1. So that means that g of x equaling x is a good, basic, simple function to use for the right-end behavior model. What about the left-end behavior model? Again, the function f of x is x plus e to the negative x, and they asked us to use, in this problem, h of x is e to the negative x. Once again, we can separate the two of these out, and we will get x over e to the negative x plus 1. Well, once again, as we substitute in x going to infinity, x getting very, very, very large, then this problem here, what we have here is that x, or that part of the problem, will go towards 0, so that our limit, again, will be equal to 1. Well, what that tells us is that that is a good, basic, simple function to use as the left-hand behavior model, because the limit does, in fact, equal 1. Well, now it's time for you to try a problem. So the problem I'd like you to work on is find a simple, basic function as a right-end behavior model, and then find a simple, basic function as a left-end behavior model for the function y equals x plus the natural log of the absolute value of x. And one hint in this particular example is, when you find a simple basic function that's the right-end behavior model, it is possible that you will use the same function for the left-end behavior model. You don't always have to have two different functions. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Okay, let's find out how you did on this. This is the problem, y equals x plus log of the absolute value of x. And what we're looking at is trying to find a simple, basic model for both the left and right-end behaviors. And what I'm going to suggest is we just use the function of g of x equals x for the right-end behavior model, and h of x equals x. So for both cases, I'm going to use the same one. So once again, here we can say x divided by x is 1 plus the natural log of the absolute value of x over x. Now, as x goes to infinity, it is true that both x and log of x go to infinity, but the log of x goes much more slowly than x does, and therefore this will go to 0. And that leads us to say that this limit is equal to 1. All right, so let's look at the bottom one and say, okay, again, this is equal to 1 plus the natural log of the absolute value of x over x, which is therefore the same thing, and we can say, yes, of course, that limit goes to 1. And so, in this particular case, we can use the g of x equals x and h of x equals x as models for the right end and left end behavior. Okay, so in this particular lesson, we learned about limits, the properties of limits, and applications of them. Make sure you work the exercises that your teacher assigns, and we'll see you next time.